electricity, solar energy into electricity. On the organizational matter, I would like to let you know that we are recording this session. So this group is now has 9 active research projects who are currently running, and they include more than 350 international experts who are coming from all over the globe and are participating in this program. On the left-hand side, you see our last year's meeting where not only the task but also the executive committee were meeting in Adelaide, Australia. And one of the main deliverables are technical tasks, technical reports, and they are done by the different task groups. And the workshop is also one of the deliverables we are producing in this task. So our members, in terms of countries, you see here on the right-hand side, they are covering all 5 continents and more than 35 countries, but also industry associations are a member of PVPS. So the mission is actually to serve as a global reference for PV, not only in terms of policy and industry decision, but also to accumulate a global network for expertise in order to have information exchange and analysis. So Task 13 also uses this international collaboration to provide guidelines and recommended practices for different applications. And to give a short overview of the current work program of this task. So we had a 2-day task meeting here at NREL and were kindly hosted by the colleagues, namely Silvana, and had a very fruitful meeting. And our phase goes until the end of next year. So in the first subtask, we are looking on reliability issue of emerging technologies, material, components. We are also working on the performance and durability of PV applications. And in the third pillar on techno-economic key performance indicators. And so this collaboration includes more than 180 experts and contributors in 25 countries. So in our first subtask, we are dealing with degradation issues of different technologies, also on materials such as backsheets, and the impact of different test strategies and under specific climatic and load conditions. And we are also working on the requalification, repair, reuse of second life PV. PV and storage is a new topic this group has taken up. And here we are also collecting data on the performance, on the degradation, but also on estimating the lifetime of PV and storage systems in order to develop guidelines for O&M in the field. In the second part, the applications include floating PV systems. So here we are mainly dealing floating systems on onshore applications, looking for degradation modes and performance loss rates, but also for yield estimation. Agri-photovoltaics is another topic, and bifacial tracking systems and modeling the bifacial tracking systems, including performance and cost issues. In the third part, the key performance indicators, we are dealing with extreme weather events and the impact of key performance indicators. And first of all, how can we diagnose these failures? How can they be repaired and mitigated? In a second activity, we are looking for best performing technologies, components under different climatic conditions in order to develop guidelines for module selection and system design. And this is what you will hear about in the next 3 hours. So we will have 2 sessions dealing with exactly this topic. And if you are interested in our work, you can read the first 2 published reports are available. So for example, the best practice for the optimization of bifacial photovoltaic tracking systems is published. So you can go to the website or scan the QR code and you will find this and previous reports under the address which is listed. And with this, I would like to thank you for your attention. We are now starting the first session, and I would like to hand over to Leonardo Micheli, who is your chair for the first part. So thank you.
Ulrike. So hi, everyone. I'm Leonardo Micheli from Sapienza University of Rome. It's my honor to start this first session of the workshop. Let me first thank NREL for hosting us, Silvana Ovait for organizing it, and everyone that is attending. So our first speaker today is Gabi Friesen from SUPSI, Switzerland, and she's gonna give a talk on the optimization of module system design for specific climatic and environmental conditions.
So, that's the micro. Hello and good morning or good afternoon, depending where you're from. I'm Gabi Friesen from SUPSI in Switzerland, and I want to give an introduction about this workshop on with the title Adapting Solar PV Solution for Climate and Application. So PV is today more and more present all over the world and in almost all climatic zones, with the increase also in less explored areas as high latitudes and high altitudes. The degradation rates differs independent of the climate where the modules are installed. And theoretical studies and field data tells us that the average degradation rate of moderate climates corresponds to the typical degradation rates which are stated on the warranties, which are in the range and average of 0.5% per year. And but deviations from this are expected when we install the modules in different climates. Tropical climates present actually the harshest condition due to the high humidity and the high temperatures, whereas in desert and steppe climates, there are present high degradation rates due to high daily temperature changes. And we observed and called in polar climates potentially lower degradation rates. And the total degradation rates we observe are a combination of thermomechanical, photodegradation, and hydrolysis degradation, as shown here on the maps of the study. This calculation, however, does not consider some of the major effects also, as for example, soiling in the desert climates, UV, snow, and wind, which affects strongly then the reliability. Climate-specific module design and testing help so to increase the reliability of the systems. But there's a lack of field data from some areas allowing for realistic climate-specific degradation rates. A further challenge we have to face is then also the increase of the occurrence of catastrophic events due to climate change. With the drastic reduction of the cost, the integration of PV also in other fields of application is getting always more attractive and convenient. Whereas some years ago, we talked only mainly on building integration and some first infrastructure integrated PV. Today, we talk also about agri-PV, floating and vehicle integrated PV. It's getting always more attention. Module design has been therefore to be adapted to fit these different needs. Examples are, for example, colored modules for the building integration, curved and lightweight modules for the vehicle, and semi-transparent modules for the agri-PV. The integrated modules has to fulfill multiple functions and safety requirements, which are higher respect to the ground-mounted. An example is, for example, the thermal insulated property of BIPV facade elements and fire requirements. There are some gaps in standardization which has to be identified and overcome in future. Also, the complexity of the system design is increasing with respect to ground mounted. And in general, there's a lack of field data also here about the field stressors of some of the application types, like, for example, floating, and very little is known about the specific degradation rates there. And I want to bring also some experience, an example of the situation in Switzerland. In Switzerland, we have a lack of flat open space, with today now nearly 90% of the installation on buildings, with approximately half of it on industrial buildings. So it's mainly BAPV, so applied, not really integrated. And 12% are actually BIPV systems, which is high in respect to other countries. And there's a very small part still of facades. Agriculture PV is also slowly gaining traction in Switzerland, and we expect more in the next years. Besides this, Switzerland the last years started Alpine Offensive, the government, to subsidize up to 60% of large-scale power plants costs in the Alps, which generate at least 10 gigawatt hours per year, and a winter production of at least 500 kilowatt hour per kilowatt in winter. These systems has to be built at above 1,500 meters and should be launched by the end of 2025 to be subsidized. There are today around, you see on this map, idea about the location of the systems. There are around 15 systems currently planned, but at this stage, very few projects are already in construction phase. So we will see, collect the experience over the years. And here shown one example of a 19 megawatt system to be built at around 2,000 meters. Within a national collaboration in Switzerland of Swiss universities of applied science, we are collecting and disseminating know-how on these Alpine PV systems to support the different stakeholders. Another challenge in Switzerland is facing is the drastic increase of hailstorms over the last years, with a huge amount of damages. And actually, as SUPSI and our laboratory, we are active in all these three fields to support the manufacturer in developing more reliable products and to improve the related testing procedures. In particular, for the hail, we are collaborating with the Swiss building insurance to better understand the consequences of hail damages and possible mitigation measures, which includes the validation of the hail testing procedures and the representativeness of the laboratory test. One of the key questions is which of the module without glass breakage subjected to the hailstorm should be replaced to avoid some later safety or high performance losses. Within the IEA Task 13, different technical reports are under preparation. And so today talks are related to different of these reports. So one of these concerns the degradation modes in new PV cell and module technologies. And the technological changes and the combination of more at the same time were introduced into the market very fast over the last years without sufficient field data. The focus was set on the optimization of module efficiency and cost without looking sufficiently at what impact these changes have on the reliability. This led actually to the increase of degradation in or failures observed in the laboratory or in the fields. Some examples as the UV degradation and contact corrosion in TOPCon, or moisture-induced degradation in heterojunction, glass breakage, backsheet cracking, and UPAD degradation modes will be described in this report. And we will have today one talk about the degradation patterns and phenomena of backsheets from in diverse climates. Not all of the observed failures are predicted by standard module qualification tests, and the subtask 1.3 report is giving an overview about the existing testing approaches and what climate or application-specific testing approaches exist. Here shown is an example of a monitoring station for the pre-assessment of an alpine system, and the acquisition of this kind of stressor data is then also the base and very important to defining appropriate test procedures. Test sequences are proposed then, for example, for hot desert climates, to include the there occurring harsher test conditions to be able to better test the climate-specific modules. The correlation of the proposed indoor testing to field performance is then to be proven. And we will hear today, one of the talks is about combined stress testing, simulating the different climatic conditions. And once knowing the failures and how to test for it, modules and system actually can be designed to withstand the harsher test condition. The two reports in 3.2, subtask 3.2, which will be published in 2025. The first will present the strategies for the optimization for the different climates, and the second then will focus on building integration, agri, and floating PV. The load-specific design of module is, of course, a balance between the optimization of the yield and lifetime, the reliability, and the increase of costs for the manufacturing. In the system design, operational and maintenance costs has to be considered from the beginning to limit then later cost or damages of the modules. In the case of integrated PV systems, not only the energy-specific key performance indicators are of importance, suggesting the use of multi-dimensional performance ratings, as proposed already also by task 15, which deals with BA building integration of PV. Economic, environmental, and visual KPIs are key for building integration, but also reliability should, of course, not be neglected. System design is strongly depending on the site morphology or the type of ground and type of infrastructure where the modules wants to be integrated. And site assessment or collection of pre-existing data is very important for utility scale systems. The pictures gives an idea of the variability you have in the field of alpine PV systems, for example, and mounting configuration which exists with specific mounting structures for each, and actually mounting structure are a key element of most systems types, with a strong impact on the cost, of course, but also on the reliability. And it's as important, so also as PV modules. Four of the talks today will present on how modules can be adapted to better respond to the specific requirements. And the last speaker then will share his experience with the alpine floating PV system. So to conclude, the technology trends towards higher efficiency and lower costs are drivers for the integration of PV in new environments. for example, for the BAPV and the infrastructure integrated PV, and for the newer ones, floating, agri, and vehicle integrated. And this supports also the numerous innovation in module design with colored, lightweight, or curved modules, for example. But the module environments are getting more challenging and testing also more complex. And the field experience is partially still lacking behind, leading to an increased number of failures we can observe in the field. We have therefore to talk more about the reliability and share the field experience. And yeah, with this, I would like to actually start, hand over to the speakers of this workshop. Thank you.
Thank you, Gabi. Let's see if there are any questions in the room. I don't see questions here. There are no questions online. So we can move to our next speaker for this session, which is Gernot Oreski from PCCL Austria, and he's gonna give a talk on adapting module design and BOM for harsh climates. Please, Gernot.
Okay, good morning, everybody. And before we start discussing how we adapt module designs, we should understand what is harsh climate. And this is a picture I took 2 days ago at our very nice evening. And we had this, whatever this is, chimney with the flames. And then the waitress brought us the polymer cups, the plastic cups with iced water. So what kind of harsh climate does this cup is this cup exposed to? On the one hand, it's the flames going very close to the cup, heating up the outer side. The inner side is cooled down by ice, so we have a significant temperature gradient, meaning the polymer just expands differently, just within this cup. Yeah, and in the worst case, it can start to burn, but that's not degradation anymore, I would say. Nevertheless, how do we translate this to photovoltaics? Gabi already showed these very cool world maps. Yeah, we have different climatic conditions worldwide, and some of them are, let's say, less healthy for PV modules than others. Especially the outcome of this paper from Julian and Ismail was, yeah, tropical regions are the worst. So what do we need? What do we need to know in order to make good modules? And basically, yeah, first, we need to know where we build our system. So what's the climatic conditions of the system or of the location of the system? Then what does it mean? What's the microclimate of the PV module depending on the location? What are the corresponding stressors acting on the PV module? What is the material response of each material, each component in the module? And also, do we have any experience with failure modes that can help us build better modules? So when we look at failure scenarios of crystalline silicon PV modules, so this is an old Task 13 graph from 10 years ago already. And I think it's still quite actual and quite state-of-the-art. And you see especially wear-out failure, but also midlife failure is strongly dependent on the microclimatic conditions because degradation behavior is influenced by the microclimatic conditions, but also PID, for example, you need a certain amount of humidity in your module. So it's not just happening like wrong installation, glass breaks, or the frame breaks or stuff like this. Yeah, and all these interactions are very complex. And to be honest, I could talk possibly the whole day just about this diagram that you see up here. But I only have like 15 minutes for my talk. So I will just focus on, what's the material response to stressors and specifically what's the material response to the stressor temperature. But if you're interested, we can spend the whole day discussing these interactions. We try to depict here in this review paper on photovoltaic reliability. So Material response. And PCCL stands for Polymer Competence Center, so we'll focus a little bit more on the polymers, because my experience is in most cases, except for the cable connectors, polymers are the root of all evil in PV module degradation. Be aware, there are two types of effects. You know, it's not just degradation effects. These are long-term effects. It takes time for materials to degrade. There are also short-term effects of your stresses. So what are we talking about? Yeah, you heat your module up, you will have thermal expansion of the different materials, and they are quite different. Polymers try to expand by a factor of 10 higher than like the glass or the silicon solar cell. Yeah, when you have high temperatures for many materials, that means you have a reduction of the modulus and tensile strength. When you go to low temperatures, for many materials, we have a reduction of impact strength. Also, when you reduce the temperature, yeah, dew can form on your PV module. Long-term effects are material degradation and fatigue, especially when you have temperature changes. It's always like expand, shrink, expand, shrink. So meaning you have a cyclic fatigue load on your PV module that can lead to, for example, delamination or breakage of interconnection. Yeah, and with two a little bit associated in between is also soiling, because you need this dew effect in order for soiling to really cement, but yeah, it's something in between, short-term and long-term. So when we especially look at the polymers that hold together a PV module, you need to be aware of this. All polymer properties are time and temperature dependent, meaning like the elastic modulus can change over few orders of magnitude in its value, just depending on the temperature. With different areas, different things are happening on a molecular level. I will happily explain everything to you, but that again is something that would take a whole semester at university to do that. What is important for PV modules? Encapsulants. You know, usually they're flexible, low modulus, very elastic behavior. Let's go to, but when you go to low temperatures like -20, -40, the modulus can increase by a factor of 3 or by an order of magnitude of 3. So like the EVA usually has like 10 megapascal or lower at room temperature and at 60 degrees Celsius, but at -40, it has like more than 1,000 megapascal. So meaning when you have stresses acting on a module like snow loads, these are directly transferred to the cell with much higher impact on the cell than it would be at 60 degrees Celsius. So when you have high latitude PV modules, you can, yeah, you should probably select an encapsulant that has also a low stiffness at low temperatures if you want to prevent certain damages. There is another effect, ductile brittle transitions, meaning at a certain temperature, polymer is ductile, but when you go to a deeper temperature, it becomes brittle. Again, what's the impact for PV modules? Yeah, some backsheets have this effect. These are some tensile test curves we measured for a polypropylene backsheet and a polyester-based backsheet. And you clearly see when you go to -40 degrees Celsius, the polypropylene backsheet loses its ductility. So it really gets very brittle. Another effect we see, the polyester performs quite well at low temperatures, but it's a laminate and we saw delamination during this test. So also this is an effect of low temperatures. So what does this mean overall for our PV module? As I already said, stresses can be transferred to other components. This is a simulation that we did a few years ago for shingled solar cells. And we wanted to see what's the impact of the encapsulant on the stress of these shingles. And you could clearly see, especially at low temperatures, when you have a high stiffness encapsulant, you get much more stress, especially in the solar cell. Not so much in the ECA, but really in the solar cell itself that could lead to breakage. Yeah, what else is temperature doing? It's influencing a lot of other properties like mass transport, water vapor transmission, oxygen transmission, acetic acid, or other low molecular compounds. The formation behavior is also strongly affected by temperature. It follows usually Arrhenius' law, meaning when you increase your temperature by 10 Kelvin, usually you have a doubling or tripling of your reaction rate or permeation rate within. So keep that in mind when you measure water vapor transmission at 25 degrees or 38 degrees, as is it done in most standards, and with the MOCON devices, for example, that may not be representative for a 65 degree Celsius operating temperature. Yeah, other effect, it increases degradation itself. So this is a nice picture of a PV module that had a hotspot, so one broken solar cell, I guess. And on the back, you see locally above this cell strong discoloration and cracking of the backsheet. So we had potentially 20 or more than 100 degrees here. So really strong local oxidation of the backsheet material that led to cracking, and in the worst case can lead to arcing and also fire. It also influences other degradation modes, for example, like hydrolysis. So here it's like a polyester that we expose to different temperature and I would say climate chamber loads with different humidities, and we measured the molar mass. And you see just temperature alone doesn't make anything to the polyester. You increase the humidity, you will see an effect, and the same, I would say, reaction kinetics. 10 Kelvin more, double the reaction rate. But also when you notice the temperatures, when you have 65 degrees Celsius and 85 degree relative humidity, not much is happening. So that's also one of the reasons we never found, or we usually don't find polyester hydrolysis in PV module backsheets, because the temperatures are just too low, or there is never simultaneously 85 degrees Celsius and 85% relative humidity. So how to adapt modules? So do we understand all of this? Then we can go and build a puzzle. Because what we need is basically this. We have a lot of small pieces that we need to put together to get a resilient module. Starting with, okay, where do we have our location? What cell technology is the best for this location? For example, depending on the temperature coefficient you have when you want to optimize yield. Depending on this cell technology, and we know the newer ones are a little bit more sensitive than the older ones. So are we sensitive to light-induced degradation, light and elevated temperature-induced degradation, UV degradation, humidity? You need a packaging concept. So then you have your design, sorry for that. Design choices. Do we do glass-glass or glass backsheet? Do we need an edge sealant? So that's depending a little bit on the mod, on the cell types. Yeah, size. If you go to high altitude or high latitude, you have snow loads, maybe build smaller modules. That helps than the bigger modules. Also the cell layout, bypass diode layout, anti-shading behavior, stuff like this, interconnection technology. All decisions you can make in order to make better modules for the specific load conditions. Yeah, and then you go to the other materials and components. Yeah, you should do a load-dependent material selection, depending on the material inherent stability, UV protection for other components, on mass transport, etc. So meaning, when you have a very humid environment, maybe not select the most sensitive materials towards humidity. And the same is when we need more UV protection, then take a UV blocking encapsulant. But you also have to check material and component compatibility and add functional layers if needed. And again, you need to test. Yeah, to summarize, there is no simple solution. And I'm very sorry, I cannot tell you how to make optimum modules for any harsh climate. You need to know a lot about the climate, the microclimate, the interaction between microclimate, module design, the bill of materials, and the interaction between the materials. The fun thing is we know how to build resilient modules. We have a lot of old modules out there that show just minimum power loss over 30 and more years. The thing is, these modules don't have much in common with modules that we observe or that we have out now, that we build now. I would say, I discussed this with Josh and Anna in the morning. Yeah, they're more robust, they're over-engineered. You know, we're talking about 4 millimeters and more glass thickness, 700 microns wafer thickness, 400 micron interconnection thickness. So they were more resilient, more robust. So we know how to build it. What's the biggest obstacle here? Probably cost. So what do we need for adapting modules to harsh climates and to make them really reliable? These are points I will tell a lot of times. I have told a lot of times, we need transparency of the module design and especially of the material composition. We need traceability of all module components. You know, something that is common for car industry, microelectronics industry is not very common for PV industry. Yeah, and we need comprehensive qualification procedures for module design and composition, and not changing the module design every other month because we got a new material or something cheaper, because that's not the way to create, I would say, resilient modules. With that, thank you very much. And yeah.
Thank you so much, Gernot. Very interesting messages. Are there questions in the room? So meanwhile, we have a couple of questions online. The first one came quite early. Is there a hysteresis in the modules when it comes back to higher, lower temperatures? Are there long-term damages, issues? This is from Jasmine.
Hysteresis by meaning when you already, you know, all the time cool it up, down, and even small variations, like when the sun is clouded or not, that change like the thermal expansion behavior. So you have some sort of fatigue load. I wouldn't say it's in hysteresis, but you have constant changes and constant stresses in the PV module.
Okay, thank you. And then we have a second question from Cas. I'm building an Antarctic solar power rover with the VI PV to drive on transverses autonomously. This means minus 40 degrees and harsh dry winds causing whiteouts. What would you say are the main points of failure in such system?
For Antarctic, yeah, I would say it's mechanical failure, because I think Carl showed it quite well. Degradation is nearly to zero because the temperature is so low. It's mechanical failure, and probably by the choice of your encapsulants, you have more or less probability of cell breakage and stuff.
Okay, there is one comment coming up. We will address that also in the panel, but if you wanna say something about how do you think is actually feasible to produce modules, depending on the local climatic conditions.
Unless the industry changes, it's not feasible at all, because nobody wants to take money and do that. So,
okay, let's thank again the speaker. And our next presenter is joining us online, is Michael Gilliard from Central Tension in the US, and he's giving us a presentation on adaptive glass to various PV applications. Hi, Michael, thanks for joining.
Hi, hello. Can you hear me okay?
Yeah, we hear you well.
Okay, great, excellent. Let me pull up my presentation.
Perfect. We see your slides in presentation mode. So
you do, great, excellent, excellent. Well, nice to meet everybody. My name is Michael Gilliard, and I represent my company, Central Tension. My background is in glass science and glass engineering, and I'm going to talking to the team, give you a short presentation just on segmentation and adaptive glass for various applications. Oh, there we go. So within glass world, I'm going to talk a bit about adaptation within PV. In pure honesty, I'm fairly new to the PV industry. My background has primarily been in consumer electronics, automotive, and some architectural. But just to give you a sense of sort of like where the future is, I think architectural is quite an amazing application to show adaptation of glass materials as well as products, and adapting those for various climates, which is not done so commonly in the solar industry. I wouldn't say it's sort of, there is some adaptation that I've seen in my short time. But just from a baseline construction, I'm sure you guys are mostly aware, there's low iron soda line, patterned or rolled glass, which is most common in PV. There are some float applications or floated glass applications, thermally tempered and laminated to encapsulate the cells, and then sometimes an anti-reflective coating on the top side. From the adaptations that I've seen in the industry, glass thickness is probably the biggest lever that the team and the supply chains have used in order, if there is an impact issue or a strength issue, just increase the glass thickness, which is definitely a great lever to use. It's used in architectural and automotive and consumer electronics in order to prevent the glass from going into tension. However, it does come with its negative sides, but it is a lever used today if people go from 2.2 modules to 2.5 or 3.2 millimeter glass. I think it is sort of a lever. However, it can be overused, and part of the goal today for me is to maybe introduce you to a few other levers in the glass industry that could be used to disrupt the supply chain. Definitely framing, how it gets framed, the overall stiffness of the frame is an adaptation that I've seen in certain areas where people are using different types of extrusions from both a sealing and a structural perspective. And then recently, I've been spending a decent amount of time in hail-resistant modules. Trackers and stowing is absolutely an area that has shown effectiveness for adaptation. So wouldn't want to leave you that the PV industry is not adaptable. However, given when you look at the architectural industry, it is full of adaptations for climates. So there are very much a substantial amount of commercial and successful products that are specific towards different climates in the architectural industry. And given the glass scale for PV, I think sort of segmentation and adaptation in PV, you have a huge amount of scale coming, which means you can adapt certain areas or sort of maybe refine products that are specific to climate. So specifically within architecture, structural glazing, there are, especially in the skyscrapers as well as large areas of using significantly larger pieces of glass. The construction of the glass, the interlayers used, the wind loads on large skyscraper buildings significantly affect the type of glass that's used in that versus a smaller building. They, as well as hurricane and earthquake resistance, there's specific interlayers as well as glass chemistries that are used when the requirements deem it appropriate within building and construction. From a performance perspective, the thermal insulation and thermal coatings are used predominantly across the industry. They do add value into or cost into the glazing, as well as the insulation value of the glazing, but there's a significant difference between the buildings in your, the glass in your large buildings and the glass that you have at home in architecture. So not one size fits all when it comes to thermal performance, both optics and strength. Just from an adaptation perspective, most glass is all about the same modulus. So you're not going to change the stiffness unless you change the thickness of the glass, but you can significantly affect the strength of the glass by various tempering processes and strengthening processes that are used in the middle. And then mounting. In my previous talks, I sort of laid out some very clear glass breaks in tension and from pre-existing flaws. So within the IGU, the insulated glass units, the cross-section there is quite a complicated, complex cross-section for both sealing as well as for keeping the glass out of tension. And I think during some of the high wind loads and details, there could be significantly more amount of engineering put towards the mounting systems that are used in PV for specific applications, for instance, high wind applications or load bearing applications, snow loads, etc. And I'll go through a couple of cross sections there to discuss the need for that. But for hurricane resistant glazing, it's sort of a hot topic now based on the weather patterns. One of the interesting areas this is specific to not only the glass thickness, but the polymer used in between for the encapsulant within hurricane resistant glazing. Most of the performance is not necessarily to allow the glass not to break, but it's to retain the structure of the glazing after it breaks is where the technology here. The reason I wanted to mention this is not that this is the best interlayer for a PV system, but this is the ionomer, which holds, it's over here in the, if you can see my cursor, the ionomer or the plastic that's in between the two pieces of glass. Not all plastics are the same. It's a significantly higher priced, lower volume product, but it has a huge amount of modulus compared to the PVB interlayers or a floppy interlayer that is most commonly used in automotive and architectural. When the glass breaks, it becomes a noodle and just falls apart, or without encapsulants, a tempered glass falls apart. The reason I think this is important just to mention on the picture graph here is the structural layers for a laminated glass system. If you could imagine this being the backside glass and this the front side glass. Within hurricane-resistant glazing, this laminated piece could be up to 5, or ballistics or safety rating could be up to 5 different components. And again, those drive cost and limit the commercial scale, but they're not used for every glass application. They're used in very specific climates that require this type of scale. So if you could imagine high wind load or multi-strike glass, so if it does break, that the whole module doesn't get affected. This is one of those areas where we could explore alternative interlayers as an example that would increase performance. When you look at structural glazing, I think there's been huge amount of increase in both the flow process that was invented in the 60s to do large scale glass, but also mechanical engineers got more comfortable with, She&P got more comfortable with the ability to have glass be a structural component in buildings. So early architecture was small windows because they don't want to cut holes in their structure. And now since then, it's been a huge amount of advancements within using large glass facades that hold a structural component for the buildings. In the cross section here, one of the takeaways that I would want you to take away from here is that the seal and the structural load are 2 different things within a IGU application typically. There's also a seal that goes between the 2 pieces of glass. That's a water and edge seal. But again, for your application, when you look at a PV system that has a frame or extrusion, you're asking the seal as well as the load carrying load between the metal and the glass typically are the same thing, the same type of material. It's like either a squirted in urethane or silicone type of seal. So this is and again, this isn't used everywhere, but in structural glazing, there's a huge amount of mechanical work that goes on to how do you keep the glass out of tension when it sees a huge amount of load? Where is the load bearing structures? And then how do you install it into the system? And the primary objective here is just to keep glass out of tension inside of these engineered areas. So I would say, like, if you looked at the framing in a PV system for a high wind load application, it's likely not going to be so highly engineered for those specific ones where the mounting matters in glass reliability. I put some of the all glass facades that are new into the industry, as well as glass stairs, where again, sort of you're using glass in certain areas, but the construction and the attachment mechanisms in these applications are significantly engineered for it. So the takeaway there should be, I think the frame and mounting systems for specific areas, hail resistant, high wind load, even high snow load applications. The science may not be just in the glass, but in the framing system that goes over it. And not necessarily the tracker. This is an impact resistant or structural framing system that could be done. And then within thermal performance, I think this is probably within glazing, obviously if you look at a skyscraper and you're seeing a reflective pattern on it, most thermal engineers want to reflect. They would love a mirrored surface so you could just reflect everything and not allow things, but you need some level of daylight to come in, some level of optimized solar heat. So for cold climates, the coatings that are used in a structure are much different than a hot climate, where you would have more of a highly reflective glazing in a hot climate and a more of a transmissive glazing in a cold climate in order to take advantage of heat. These ones are interesting because it may not affect the glass thickness, but it affects the coatings put onto the glass. And you can see ultraviolet in there. One of the sort of the thought processes, especially when we look at degradation that I would have, is these coatings are tended to be put on the backside of the outer glass or the inside surface of the inner glass, where you're protecting the coating from the environment. But for instance, your first weapon would be reflection or highly absorptive. If UV like glass degradation or polymer degradation tends to have heat and UV associated with it. For instance, if UV is not that big of an adder for solar efficiency, maybe in certain climates, you could look at highly transmissive visible infrared UV rejection coatings or highly absorptive coatings that are used in architectural for layer 2 or surface 2 on the glass. And again, not for everywhere, but for specific climates. I think it could be quite helpful to look at those. And those are used in certain areas that again, it does add cost, it adds complexity to the supply chain. But if within the PV industry, it sort of has this sort of like one size fits all the attitude, if you will, or supply chain focus. If you look at the outside of thickness or the adaptive that I mentioned, as the PV industry scales and more glass is used and additional plants come up online, it may be an interesting concept to start to look at segmentation of those coatings. And here's just sort of my, like within glass durability or glass breakage, that tends to be the reason glass gets put over it, where you'll have some level of failure that'll show up. Within this industry, I do think there's quite a significant amount of work, both on the again, you could do the glass thickness for sure, but interlayer materials, coatings that could be put on it, top surface coatings that would remove, for instance, allow for snow removal easier, that could be added on or introduced into the supply chain with that much difficulty as far as secondary operations. So thank you very much for your time and your attention. If there's any questions, I'm glad to take some questions.
Thanks so much, Michael. Yeah, we have a question in the room. Please introduce.
Hi, Gernot speaking, speaker from before. You said there are many coatings available, like UV retention, heat retention coatings. What's the long-term experience with them? I'm just interested. So are they like degrading like anti-reflective coating over some years, or?
They tend, most coatings that I'm familiar with, if you have an anti-reflective coating, you would want to put that on surface 1, so the top surface of your module, to prevent reflection there. So that would be like kind of an exterior coating, which has degradation, for instance, from environmental, thermal, abrasion, etc., that goes onto the top surface. Most of these coatings, as far as reflection, so if you look at a skyscraper and you see it to be a gold reflective color or a blue reflective color, those coatings tend to be put on the backside of the outer glass. So what we call surface 2 in the industry. So it's protected from the environment by the outside piece of glass. So for instance, if you looked at a specific reflection coating, it likely would be applied to surface 2. If you looked at an anti-soiling coating or an AR, you would put that on surface 1 or the outside surface of the coating. But these reflection coatings tend to be buried in the stack to be protected from environment.
Michael, we have a couple of questions online.
Sure.
Is central tension working on any non-glass transparent material for PV?
Actively, no. I do have a background in polymers and polymers, as well as like highly transmissive polymers from both automotive as well as in my background in materials. I think on the potentially on things like within, for instance, hail resistance of sheets or peel off areas, the areas that could be more highly resistant. If you look at the UV requirement as well as the structural requirement itself and flatness, cost, etc., glass, I think there's still a lot of room in glass. But I do work a bit in non-glass transparencies.
Okay, thank you. And a quick comment, if you can, if you could just comment on load cumulative stresses from repetitive heats from hailstones.
Yep. Yeah, so this has come up a bunch. So within as far as like, does glass get weaker if it gets punched a lot or hit with a hailstone? It tends not to from that specific area. If you're below the K1C or the stress of crack propagation, glass tends to be fairly robust. However, there's other impacts over time that can start to look at crack propagation. So, but it doesn't necessarily, if it induces a flaw, for instance, like on the edge of the glass or between the frame and the glass things, you can definitely weaken glass and create new flaws. However, if you don't create new flaws, glass doesn't necessarily have that fatigue behavior that if you hit it a bunch of times, it's pretty happy, especially strengthened glass, as long as you don't exceed the load for crack propagation.
Thank you, Michael. Unfortunately, in the interest of time, we have to go on, but there are several questions are coming in the chat. So thanks so much for your interesting presentation. Our
My
next
pleasure.
speaker.
My pleasure. I'll be on as well for later on for the.
Thank you.
Yep.
Thank you. So our next speaker is Peter Ake from NREL, and he's going to give a talk on combined stress testing, simulating different climatic conditions.
Okay, there's a clicker if you want.
Thanks for the introduction. This talk is combined stress testing, simulating different climatic conditions, subtitled How Always Testing at Extremes May Miss Things. Thank you for your introduction. Yeah. So an introduction to what combined accelerated stress testing is. We have to and why it exists. Its purpose for being is that numerous field failures are seen in PV modules that pass qualification testing. And we create mechanism-specific tests only after the failure mode has been found in the field. Numerous parallel tests are getting time-consuming and expensive. PID, LETID, UVID, we create new tests all the time. Stakeholders are considering buying into new technologies, and they see risk of new technologies, risk of small incremental changes, risk from failure of critical parts. And with respect to the standards we create and tests we create to ensure modules' durability, so this presentation is auto-advancing again. I'll see what I can do about that. But it's a large... Yeah, so with respect to the standards and tests we make, we seek more objectivity because tests only come about when people notice a problem and people want to do something about it. And there's all kinds of politics involved that prevent things from moving forward sometimes. People deny things really exist until it gets really, really big problems sometimes. So it's a psychological barriers sometimes impede progress. It's a big industry. Risks as well as benefits are substantial. Testing apparatuses, making new apparatuses are always a challenge. So addressing this, we have proposed and developed combined accelerated stress testing. So the idea here is not to have some kind of a priori idea of what's going on, but to be comprehensive in representing testing. So the sample should be as representative as possible as the shipping product. We're still in prototype stage, so we're using mini modules. The stress factors we apply should be extensive to as much as possible, include the stress factors of the natural environment. The combination is a little bit of the focus in my slides today. And what we're trying to do here is be representative of the actual combination and sequences of stress factors as they occur in the natural environment and their balance. So that includes the seasonal, climatic, and diurnal cycles that nature provides. So we've got to capture that. So the way that exists in the current manifestation of combined accelerated stress testing looks like this. There's winter, which is kind of like a cold storage, but applies dynamic loading. There's a spring cycle, which the module reaches modest temperatures of about 25 degrees C, 35 degrees C, with modest amount of illumination, like 0.8 suns at maximum. The module experiences freeze-thaw cycles. Here, tropical. This is based on previous standard ASTM D7869 developed for the paint and coatings industry. And this is the longest stress cycle, which is essentially mimicking the tropical climate. And this high desert, which is hot and dry, and with hot days, cold nights. And that's what we're trying to accomplish here. So with this, I've got 3 examples for you today, as shown here. The first is potential induced degradation by facial perk, and to show you how the seasons matter and affect whether we're going to see something or not. So first, a quick overview of what PID in the back of bifacial perk is that it occurs on the rear in EVA glass backsheet modules, EVA glass back modules. It occurs in negative system voltage. It's generally correlated to high leakage current when a slow but steady ionic charge moves and deposits more positive charge into silicon nitride, attracting photo-generated carriers leading to their recombination. It recovers under light soak and under opposite system voltage when we move charge back out. So that's what it is. Okay, so this particular graph is to just give an overview of the sequence of stress in samples. So again, something to note is that this green, as we've moved the power, as we examine the power as a function of stage of the test. The green is the winter and spring. The blue is the tropical. And if the colors are right, this darker blue here is the high desert. So what I'd like to point out is that in the spring, again, the samples reach about 35 degrees C, and in the tropical and high desert, the samples reach about 90 degrees C. So to point out here is that the glass EVA sample is the one that degrades as expected by this potential induced degradation. And I'd like to point out also that pretty consistently, there's variation, of course, but pretty consistently, the degradation happens after the winter, spring, and sometimes and often recovers in the tropical. So the spring is modest light, modest temperatures, but that's the sequence where we see the most degradation. And when we go to the hotter climates, the effect recovers. So this is the first example where, always testing at the extremes isn't going to explain what's going to happen in all climate. This particular chart just proves PID recovers when we reverse the electrical bias. So, okay. Next is PVDF backsheet cracking and combined accelerated stress testing. So this was very well studied by the folks at DuPont. And this particular picture is a PVDF backsheet cracking in Saskatchewan, Canada. Canada is not known for being particularly hot, not known for being particularly humid, but it's a failure nevertheless. They found, preceding me, they found that they could accelerate the test in the so-called module accelerated stress testing 1, which is graphically showed here. But I'm going to show you my experience, or our experience. So what we're going to do here is walk you through the stresses that were applied and what we observed. So at first we were applying extensively this tropical sequence. So this is hot, humid, simulating Florida, and there's really no cracking. We recalled that this PVDF, failed in Saskatchewan, Canada. So we said we better apply other seasons to it. We tried winter, we tried spring, all okay, no problem. But when we applied this desert climate, that's when cracking happened. So what's going on in desert? That's cycling dry, low humidity cycling, between low temperature and high temperature, minus 20 to 90, I think. And what's going on here is that there's a loss of humidity and there's actually shrinkage in the material. So effectively, it's this climate that brings around this, that finally brings around this change after the previous sequences. So looking a little bit more in more detail, we're looking at the cause of PVDF cracking. It's Dave Miller in the back there, did the indentation hardening. And what we found is that after when the material was saturated, the material in an indentation hardness was fairly supple, fairly soft, and the indentation ball would penetrate deeper. But when it was in the desiccated, dry, after a dry, being put in the dry box effectively, the material was harder, and the ball wouldn't penetrate as far. And that's manifested here in these hardness measurements, where the saturated with moisture material is softer. So, of course, there's other polymeric changes that Gernot went into, but there's phase changes in PVDF, and there's PMMA issues that cause the PVDF to fail chemically. So the final issue is cell grid finger failure. And what I'd like to do is walk you through these samples here, which are actually low temperature solder interconnected material through cast, and that's, say, tin bismuth. And what we did was we ran some some samples in cold only, some in hot only, and some in all 4 climates. There was speculation that maybe in the cold only you would see failure, but maybe the high temperature would lead to some recovery of the tin bismuth. And I think that does actually happen, but not in this case. What we found, in fact, is that the high temperature stresses are what led to the failure in the interconnects. And of course, the material which went through all seasons, cold and hot, did show degradation as well. So this is confirmed by outdoor measurements, where here we're looking at Arizona, here we're looking at Alaska. And what we're finding is that the hotter the sample is, such as whether you have insolation with or without, the higher the temperature, the more the degradation. That's to say, the very hottest samples with hot spots forming that can be seen in electroluminescence and thermography, you actually see the wires move. And also, in this particular sample, we're seeing a combination of not only the wires disconnecting from the cell at the edge of the module where the stresses are higher, but actually the grid fingers breaking. So, on the other hand, in Alaska, the max temperature is not so high, and we don't see any kind of such breakage in the grid fingers or the wires after 24 months. So here's a situation where the extreme temperature did make a difference, and the climate did matter. So I'm going to summarize here is that multi-season climate cast is well suited for understanding behavior in various climate conditions. And I went through 3 examples. PID polarization on the rear of bifacial PERC is most consistently apparent in the spring climate with modest illumination, because high illumination leads to recovery of the PERC PID. We saw PVDF backsheet cracking after various cast weathering, but especially in the high desert climate. And that's associated with the desiccation and the embrittlement of the material and the hardening of the material, lack of plasticization, so to speak. And finally, cell grid finger failures were apparent at higher temperature stress tests, and that the high temperatures occur in the tropical and high desert climates. That's all I've got, and I thank you for your attention.
Thank you, Peter. Let's see if there are questions in the room. I don't see questions coming online. I will just give it a few seconds. I don't know if David, So do you see any, or do you have any opinions about, I mean, in this case, you identified a failure mode in the field and then investigated a test. Do you have any recommendations for changes to qualification tests based on these things, like, or climate-specific qualification tests? Like for different climate-specific products?
Well, when you say qualification test, you mean like an IEC type situation? Well, it depends how bold you want to be. Like I would propose actually doing combined accelerated stress testing to qualify modules. Absent of that, we're kind of in a situation where we're adding yet another parallel test. And right now, what people are realizing is UVID is important, and a test is being created for that. And that's all good and fine. But the issue is, you know, multi-gigawatts have been put in the field already without this understanding. So we're still in this bad loop of, well, oh, we found, you know, an issue. It takes us a couple years to realize it. And people are, you know, wondering why their systems aren't performing as well. Yeah, we better get around to adding a test. Let's figure out how to do that. We've got to kind of convince the deniers that this is really happening. So we have about 6 years before all this happens. So, you know, that's the second best alternative. It's better than not at all, but there you have it.
Yeah. So thanks again, Peter, for your presentation, and thanks to all the speakers that have participated in this first session. We now have a coffee break for about 30 minutes. So we reconvene at 10:40 Mountain Time here in Colorado. And yeah, we'll see you shortly.
Put a slide up there.
So let's start with the second part. It's okay now? Yes. So let's start with the second part of the workshop. We will start with David Miller from NREL on anti-soiling coatings of PV modules for different climates. It's yours, the floor.
Okay, thank you. Contrary to the appearance, there's a few authors and institutions here. This is not an astronomy presentation. In PV, insolation from the sun, the temperature of the modules, and the contamination of the surface are three primary natural factors affecting electricity production. So for example, you can encounter a 1% per day loss from soiling in the Middle East and North Africa. There were examples of an 80% loss per storm from the large sandstorms. And so in our study, we wanted to accomplish the characterization of soiling, compare anti-reflective and anti-soiling coatings, and compare cleaning strategies, particularly for me, relative to the IEC abrasion standard that we have recently developed. So the topics that I'll cover today regarding soiling, we'll get into the morphology, particle size distribution, area concentration, object size, cementation and composition. We'll look at cleaning methods, anti-reflective and anti-soiling coatings. We found an interesting result from the impact and potential of the pH of rain, and then an in-depth optical performance assessment. And we did see some location or climate-specific effects. So in our study, we used 3-inch by 3-inch coupons, including anti-reflective, anti-soiling, meaning phobic and philic coatings, and just uncoated reference glass. These were put on a black backplane to achieve a similar temperature to a PV module. And we sought contamination and abrasion-prone locations, including Mesa, Sacramento, Mumbai, Kuwait City, and Dubai. We had 4 cleaning methods, which is number 1, not to clean at all, dry brush cleaning, low pressure water spray, and wet sponge and squeegee. Typically samples were cleaned monthly. In Kuwait, they clean daily, as they normally do. And then we would get back 2 replicates of each material each year over 5 years, looking at, in the microscope, like the particle contamination, in the spectrophotometer, like the optical performance, and then in forensics, like damage morphology. I'll start with the microscope images and the subsequent image J analysis. We can compare the number, area, and volume particle size distribution. The median size ranges between 2 to 3 microns, 6 to 20 microns, 10 to 30 microns. There's no standardized method that's used to analyze and report on the surface contamination. A 16 micron size was identified in a literature review that's more consistent with the volume PSD, whereas the number directly identifies the size of contamination. The volume might be compared to publications from the atmospheric sciences fields. And then we had a 1 micron resolution limit for our microscope. We're limited to examining the PM10 contamination. The one result that stands out immediately, however, is the large size in Dubai in pink, and that indicates that cementation has occurred in that location. So if we were to take a look at our coupons, the most densely contaminated places are Dubai and then Kuwait, much more so than the others. In fact, Dubai may accumulate multiple layers through the course of our study. Mesa, on the other hand, had a very disparate object size. And I'll point out the green color results from the use of cross-polarization imaging. We wanted to try and extract the most information that we could about the objects that we were seeing on the surface. Cementation is the strong surface adhesion, particularly with the dew cycles. This was evident in Dubai. It's likely in Kuwait, and perhaps occurring in some other locations. The palygorskite clay is more prevalent in MENA than, for example, in Arizona. And then we observed organic contamination where fungus is the most robust life form, if you will. It was overt in Mumbai. It was more scattered in Sacramento, and observed only in instances at the edges under the mountain frame in the desert locations. And the fungus spore transport is an intercontinental phenomenon. So for example, trade winds can carry spores from Africa to Florida. So this examines and compares the particle area coverage from the ImageJ analysis, comparing the cleaning methods. The cleaning was eventually limited by COVID in some locations, and we can compare to that the PM10 and the precipitation based on web resources. And through the course of the study, or later in the study, we chose to focus on 5 of the 10 materials that we started with. This is shown for Dubai. And here we see that the cleaning can immediately improve the efficiency by tens of a percent. So the no clean samples have like a 60% contamination. That's more like 10 to 30% if a cleaning method is used. The level of contamination asymptotes according to the cleaning method. And it's entirely possible to clean more frequently than monthly is warranted in Dubai in order to prevent the cementation. The erratic profile with time may just reflect the fortuitous timing of the sample collection relative to when we measured the samples. Then moving on to this instance is Mumbai. This is a tropical savanna climate. So there's on average 2.3 meters of rain each year. This is substantially more than centimeters of rain in the other locations. And most of the repoints actually occurred just before the rainy season. Here, the no clean is still distinguished from the dry brush and the wet sponge and squeegee, but the low pressure water spray is not as effective. And a previous finding in this study was that contact cleaning is required to really remove the fungus, which can trap inorganic contamination and magnify the effect of the fungus even being there. These are, again, coarse annual read points. So things like rain, the biodiversity, and the population of organic species can vary through the course of a single day. Now, this is to start to compare between the different coatings, and we'll compare between Dubai and Mumbai, again, using the ImageJ particle area coverage analysis. We're strictly limited to the no clean coupons in this case. We didn't want to convolute the effect of cleaning, like damaging the coatings. Coatings B, D, and G are anti-reflective and anti-soiling. U is just an anti-soiling only. B, G, and U are hydrophobic. D is oleophobic. And J is the uncoated glass. What stands out or really doesn't stand out here is that there's not an overt winner relative to just the uncoated glass substrate. So we took a little further look at that using a rank order analysis. So at each site and at each read point, we would rank 1, 2, 3, 4, 5, and then you can take and average that over all of the study in order to also quantify the efficacy of the coatings. And I'll remind that the transmittance at the top relates to the optical performance for a one-junction device from the IEC standard. The particle area coverage, this is getting at the contamination that remains after samples were shipped back to us and characterized. On average, all of the coatings improve the optical performance relative to uncoated glass as the bottom row. So you're getting more electricity. We did not do a techno-economic analysis here to identify the critical cost of the coating. The durability of these coatings is limited. The porous silica anti-reflective coatings that are typically used in PV survive something like 50 to 200 cleanings. So again, relating to the limits of the cost and stuff. When we did a rank of the anti-soiling coatings, these are not distinguished according to the cleanliness. It's essentially the same average and standard deviation. And we've seen in studies since uncoated glass may actually be cleaner than the anti-soiling coatings. And that's not to say that opportunities may not exist, but you might want to think relative to previous efforts. These have predominantly focused on hydrophobic, fluorochemical-based coatings. We can move on and look at the coating damage. There's a visualization method through oblique imaging. You can qualitatively assess the integrity of the coatings. And so for the 125 nanometer thick porous silica coatings typically used, the coating appears blue, the glass will appear brown. This is the Arizona samples after 3 years of dry brush cleaning, they're mostly scratched away. A surprise finding when we compared the no clean and the water spray samples, both with non-contact cleaning, the porous silica coating was mostly absent after 4 or 5 years in Mumbai. And possible factors here include the impact and pH of rain, organic contamination. Does the fungus can secrete acid, or just hygrometric degradation of the coating itself? And then to compare between all of the sites, the damage to the non-contact and water spray coupons was unique to Mumbai, where the desert samples are fortuitously perturbed. You can verify that the coating is actually still present there. And for Mumbai, if we look in detail between or through the course of the study, it's really the glass substrate that stands out after 4 years or so. There are islands of remaining coating that might correspond to trapped inorganic contamination that locally protects the coating. But it's really the factors of impact and pH that have come up in the local experts' research at IIT. And so an accelerated test sequence for these coatings would have to include like a UV, something like a rain test, which is identified here, and then an abrasion to evaluate the effectiveness of cleaning. And then lastly, I'll focus on a comprehensive optical characterization. So we can examine the transmittance in green, the reflectance in blue, and then the absorbance follows from those other two. We compare the final minus initial here, so this is the change through the course of the study, and we can do measurements with and without an integrating sphere to quantify the scattering. And so the things that stand out are that the transmittance is most reduced in the UV visible wavelengths, above where it becomes transmitting. This is where it has its greatest refractive index. Much of the loss of transmittance results from absorbance, and then there is some effect of forward scattering. Overall, and in most locations, the reflectance was actually reduced or negative, and the reflectance was highly subject to a backscattering effect. There is an exception in our study. The reflectance was increased in Dubai, and this is attributed to a local calcite contamination. Okay, so I've talked about our 5-year field coupon study. There's presently no standard method of analyzing or reporting the particle size distribution, which is seen to range from 2 to 30 microns. The density, object size, occurrence of cementation, organic composition of the contamination are all local or climate-specific characteristics. A preferred cleaning method, possibly requiring contact cleaning, notably reduces soiling. Anti-reflective coatings gave a performance benefit. The anti-soiling coatings were often not readily distinguished from glass. Surprisingly, the impact and pH of rain may degrade the porous silica coatings in precipitation-prone locations. And then much of the loss in optical performance comes from absorbance, with some forward scattering. There are some local exceptions that exist. So there is presently an article about this, and then the supplementary information slides. I've covered some of the highlights of the study, but there's much more that's covered here if this is of interest to you. And then folks that I would like to thank, including those that have helped with samples and shipping back to us on characterization methods, and then in the IEC standard and PV CATs, where this was a really popular topic, much more so than many of the other standards actually. And then a thank you to our sponsor. Okay, that's it.
Yes, thanks a lot. And are there some questions from here, from the room?
Do you have plans to do the techno-economic analysis? It seems like it wouldn't be that hard to do.
I think that would be a next step after this is now complete. Okay. Yeah. And we've also developed the abrasion test standard, and so our results are in many ways comparable to what we see here. So yeah, certainly kind of a next step. Yeah.
Okay, look forward to it.
Okay, let's so pass online. Yeah, I can't see questions now. And we pass to the next speaker, to Laura Brookman from Case Western University. And she will present on degradation patterns and phenomena of backsheets from diverse climate zones.
All right, thank you, everyone. So we're going to talk about backsheets and some field surveys that we have. And I'd like to thank, this is a old picture of the group, but we have two students, Raymond and Zach, who did most of the work, and a postdoc, Xuanji, here. And this was a joint effort by UL, NREL, NIST, Arkema, DuPont, and Case. And it was a great amount of work. This was actually we did a 3-year project originally, and then a second 3-year project funded by Department of Energy. So what we first did is we went out and retrieved modules. And UL was particularly great at getting retrieved modules from commercial power plants. And we retrieved about 33 modules from 15 different locations. And we got a bunch of different backsheets from these and different climatic zones from 0 to 28 years of exposures. And what we found is there was really different backsheet degradation out there from these modules. Except for what we found is we didn't really have actually a good sample set. We didn't understand why we were given these modules. Generally, they were given to us because they had failed. People didn't want them anymore. So what we didn't have was a good understanding was what was happening to the modules that were still out in the field. And we didn't have a really good understanding of where these modules were particularly mounted in the field. They were just retrieved, given to UL, and then we kind of did really nice characterizations of them. But what we didn't have is a good population of what was happening in the field. During that initial project, we went out and we had done a couple of field surveys. And we really didn't think that it was going to give us really interesting data. What we wanted students to do is understand what a commercial power plant looked like and understand that. But when we went out, this is a site at NIST, and we did yellowness index on the backside of these modules. What you see here on these edges is that there is basically, yellowness index was tending up on the sides of these modules. The ones on the outside were having higher yellowness index, and we're going to say this is a proxy of degradation. So they were degrading more than the ones in the middle. And then this blue row is this top row here, actually had extremely higher yellowness index than the ones at the bottom. So basically, when we were getting those field retrieved modules, they weren't necessarily representative of what the whole site was looking at, because we don't have the same degradation here that's happening in that site. And so we also went and took irradiance measurements, and our irradiance measurements at that site was actually mimicking this yellowness index that we were seeing there too. You notice that we had gray rock here. We don't have grass. It's going to have higher albedo as well. So basically how we were constructing a commercial power plant was going to highly impact this polymer backsheet. So we got this new project. We went out and we looked at Köppen-Geiger climate zones, but we also went a little further and thought about how much water was happening, what was the irradiance levels and those things. And we tried to do site selection. We also had to get commercial power plants to let us out on their fields, which was potentially difficult. It was stymied a little bit by the pandemic, and then by how much they shut down access was much more after the pandemic. And then we developed a field protocol, because what we got after talking to DuPont, Arkema, and UL is that there wasn't a common language about how to speak about a field. we weren't all calling these things similar types of language. So not everyone was talking about the row the same way. We weren't all talking about what was a block of PV modules. Were we talking about the bottom the same way as the top? And how do you speak about that? So we've been working with ASTM a little bit with Xiaohong at NIST about, can we make this standard language as well? And so we started talking about racks and sub rows and module numbers so that we can actually have language that is consistent along the way. This is a paper that we just submitted, and it's just under review, or just we're doing minor revisions. We also gave the students a body camera that they walked around so that we could actually be able to identify when we made mistakes on our data collection. So this is the student GPS locating themselves around the site. So we had a consistent way to label everything. So there's sub rows and rows and module numbers and a block, and not all commercial power plants are the exact same shape as well. So we did materials characterization, we did FTIR, yellowness index, gloss. We started doing handheld Raman, and there's other handheld different characterizations. They're not all cheap to do, and there would be really great way to do more advanced handheld characterizations, especially if we could start looking at encapsulants or other types of handheld analysis. With Chris Davis and Meng Ji, we're kind of merging this with some of the ELPL work as well. And then we also talked about where to measure on the backside of the module as well, so we can have consistent labeling there. And then all of this data is on OSF right now. So here's the link right there. And we really thought about verification and making this data accessible. So some of the observations that we have is we went out to 41 different sites. So there were 7 climatic zones. We went to 3 sites outside the US. So there was a Taiwan site and 2 Chinese sites that UL were able to do with their staff, which was really great. So we were able to actually take our field survey and translate it over to different individuals. We were able to actually do that consistently, that the data all transferred to us, which was really great. And we got 7 different polymer types, and this is only the outside layer. Obviously, we don't know what the inner layer is. And we were able to take about 17,000 measurements and consistently track exactly where they all were. And then some sites we went to more than once. So we went to 4 different sites more than once, so we could get temporal changes over time. So this is the site at NIST, and we will all say that PEN is not a common backsheet type, and it's very surprising that it's there. And so we're going to use it as our example only because we went there 3 times, but why anyone made PEN backsheets is still surprising to, I think, all of us. So, but what you will see is that we have 4, 8, and 10 years of exposure. And what we were able to see is, again, we have this tailing up at each side. So there's higher yellowness index at each of the edges of our modules for all years, except for, again, at this top rack at 10 years, it actually starts tailing down. So we get photo bleaching. So instead of yellowing, we're actually whitening at this 10 years. And at these modules, you actually start to see that they started cracking. So when they started past yellowing, they went to photo bleaching, we started seeing cracks in that backsheet. So this is pretty common when you can go to transition from one degradation mode to a different degradation mode. And we were able to track it, that we saw this cracks in these backsheets. So that was pretty nice. Another thing we saw is that this is a site in South Carolina, and there is really nice road on this side, or really nice trees, wonderful trees. And then in the middle, there is a road. And we saw this tailing up on both sides of a higher yellowness index on the road side. We did not see it here on the tree side. When we simulated irradiance, you get the same simulation that there's higher irradiance on the road side. They were very close to the road, actually. And you also see, we saw these really random modules with different changes in yellowness index. These are fluoropolymers, so the yellowness index is not very yellow. Obviously, they are bluish colored. But we actually went to them and asked, and they had replaced modules at these positions. And so we get this unusual behavior there. So the site was actually really kind and went through and checked for us. Another thing that when we looked at gloss, interestingly enough, these purples, what we get is that we get significant gloss loss right around the junction box. So right where it's hotter around the junction box, you see in all of these modules, there's a change in gloss around those where it's hotter, and it's measurably hotter. We went and changed that. So we see these degradation patterns, and basically the backsheet is non-uniformly degrading as a whole system. So everywhere along that backsheet itself is non-uniformly degrading, but in fact, the module itself is non-uniformly degrading in the field itself. So another thing is we try to think about all the variations that we would need to account for of a module in the field. So there's airside material, the climate zone. What does that climate zone actually mean? There's changes in irradiance, that's the exposure. That also means the row position, where it is in the field. But then that impacts the ground cover. So that gray rock was a particularly bad material to have underneath it. But we also noticed at one site, which I don't have here, the students started standing on the ground and having to kneel down to measure the backsheet. And by the end of the row that they were at, they were standing on a step stool measuring the bottom sub row. And so there's significant changes in elevation of just exactly one sub row, and that needed to be accounted for. So there's huge variations when we think about just the exposure conditions of the backside of that modules when we're talking about simulating the stressor conditions or these microclimatic zones that these modules are under. So this was Silvana worked with us on this, is thinking about doing rear side irradiance modeling on the backside of these. So for bifacial modules, you're simulating what is that albedo irradiance. So we use that to think about what is the backsheet seeing. And so we actually took what is the location, the albedo, the size of the modules, the gap between the modules and the cells, also the number of rows, the number of modules, the tilt, and then the actual TMY of every single site that we went to. And we modeled those for each of our modules. We also included where the I-beam was, because we got shading from all of those in our sites. And instead of thinking, okay, this is our NIST site with our PE and backsheet, instead of thinking every single module has the same exact dose, we can actually simulate what the irradiance is for that particular part of the backsheet of that particular module at that site. And we can actually get a much better simulation that they're not all seeing the same exact irradiance on the backside. They're getting a variety of irradiances at that site. And so we can build a better model because we have different amounts of rear side irradiance. The interesting part about that, so thinking about our YI on the back side of our modules and looking at this, is what you see here is we have a lot of PVDF. PVDF behaves very similarly. It's not changing very much. It's also generally made by one manufacturer, so you have very consistent manufacturing. If you look at PET, it behaves very wildly differently. It's not made by the same manufacturer. PET is not PET. PET has different stabilizers. It's made very differently. It has different amounts of monomer left in it. And we should not be saying that PET is PET. We need to think about PET as the manufacturer, as the locked variety that it is, because they're not behaving the same way to the same amount of irradiance that it is. So this is really important to think about this for these. We would have better modules or models here if we could go further out and simulate a dose. This is where we get a little less good in our models here. The other thing we did is we took a spatial temporal equation and we took the time of contact of wetness. So we simulated how many times we would go through the dew point at every single time at these sites. We took the time at an elevated temperature above 35 degrees C. We took our simulated irradiance material type, whether we were at the junction box, and we were able to make a model for all 23 different sites for 18,000 module or 1,800 modules and 7 different types of materials. And our model fits pretty well for all of these at the same time. So we have a pretty good prediction that we can predict our YI for these sites within this time period of our sites. So thank you very much.
Thanks a lot. I think we have time for 1 or 2 questions. One from the floor here.
Thank you for the interesting presentation. You now have the model. Yes. Yeah, so you now have the model. How far ahead do you think you can forecast, or what are, say, the next steps or next conclusions that you can draw out of the model?
So I think we can predict slightly ahead of the irradiance that we have in this data set. So we're at somewhere around 15 years on 15 years, which I think is pretty good. We're adding this to a generative AI data set that includes like performance loss rate and brands to include it in, say, okay, maybe backsheets are not necessarily causing performance loss rate, right? But at some point, if the backsheet starts cracking, are we going to maybe go to that site? So is there a point in which we predict yellowness increases to, and then we flag to say this is a site that we're concerned about? And maybe we don't worry because we know it's PDF at that point, but we start worrying because it's P or it's polyamide and know that this yellowness is I should have.
I hope they hear you online. I don't know. I saw no comments, so probably yes. A last question from online, from Yasmin, singular. Is backsheet damage primarily due to light, heat, or some other factors?
So it's primarily light, and then it's worse by water. So hydrolysis makes it worse and temperature makes it worse, but light seems to be the driving force of the initial polymer breakdown.
Okay, thank you. So I think we can pass to the last speaker, which is online. So please, Andy Kaufmann from Romand Energie, you can share your presentation. The presentation is presenting the experience with a high altitude floating solar power plant in Switzerland.
Hello, can you hear me clearly?
Yes.
Perfect. Thank you for the invitation, letting me speak at this workshop. I'm glad to present you our PV plant in the Swiss Alps. I'm working as a development manager for floating PV projects in Switzerland, even though Switzerland is not exactly known for floating PV. But as we have Alps, high mountains, we have a lot of hydropower, and as much hydropower accumulation lakes where we have lower temperature, better radiation, snow during the winter.
Can you speak slightly louder, because
yeah, sure.
We can hear you, but just a little bit sad.
Okay, is it better like that? Yes, I will try. So yeah, as I said, we have a lot of mountains and lakes, hydropower lakes in the mountains with lower temperature and better radiation. So everything good conditions for the PV production. My presentation today, I will present you the plant that we commissioned 4 years ago. Speak about the lessons we learned of it, then have a few words about the design of the PV, and at the end, some slides about future projects. Our PV plant is located on Lake Les Toules, which is in the Swiss Alps, at the southern border of Switzerland, near to France. This harsh climate conditions, we can see them on the two pictures here. One in summertime, the other one during winter time when the lake is empty. The lake variation is about, the water level variation is about 60 meters near the dam. Our PV structure is located here at the southern end of the lake. We, as I said, we are 1,800 meters above sea level. During one day, we can have up to 2 meters of snow. During winter time, we can have 60 centimeters of ice on the lake, and the temperature can vary between -25 and +25 during the year. Some technical description of the installation. The floating structure consists of 35 floaters covered with PV panels. Each of them has 40 PV panels. And the last floater contains the 3 inverters and transformer with a weather station and webcam. The PV installation, we have a row spacing of 1.95 meters and tilt angle varying during the stages, 37 degrees when we're floating, 32 degrees when the structure lays on the ground. The total installed power capacity is 448 kilowatt peaks, and we produce slightly more than 600 megawatt hours a year, which is a yield of 1,480 kilowatt hours per kilowatt peak. As I said, the water level variation is about 17 meters during the year. We have a wind load considered for the dimensioning of 42 meters per second. The structure lays on the ground between December and May, and the plant was commissioned 2019. The steep tilt of the panels is due to the need for winter power. We are in Switzerland, we are in need of winter power, so all our new large PV projects are aiming for winter power. And this angle is also due to the snow removal. 40% of our production is, as I said, winter production is produced between October and March. Here's some aerial views of the installation when the lake is full or empty. We have all our 35 floaters with the PV panels here, and the last one here to the southwest with inverter and transformer. We then have to the west electrical cable connection to the land, from where we are connected to the grid. As you can see here, the landscape, we're surrounded by mountains, some of them going up to 3,000 meters. Some lessons learned. The strings are composed of 22 or 24 modules. Each platform contains 40 modules. So each platform or each floater hosts 2 or sometimes even 3 strings, meaning that strings must connect over 2 platforms over the water. Maintenance for these string connection on the water is therefore quite challenging and different to what other FPV producer EPCs can do. As well, our platform with inverter and transformer here, especially during winter time, the access to this platform is hazardous. It's conditioned by the natural hazards we can face, like ice or avalanche danger. Some of the structural lessons. The platform on which we have to go aground during the winter time when the lake is empty, we have some instability on this platform. We have noticed some settlements, and our floaters cannot touch ground everywhere. Sometimes we have up to 80 centimeters of space between the ground and the bottom of the floating. Our anchoring system is a specific design. It's different from what other FPV EPCs can do. This special design is due to the water level variation we face. This design is working for the plant we have now, is unsuitable for larger water level variation. So we're working on an improvement of the system. And finally, the earthing system we installed has to face different states between floating and grounded. This wasn't exactly addressed during the study phases, and we had to improve this the system. Especially, we had some of the grounding components that were touching water when floating, were stuck in the ice and were ripped off. How did we design the PV installation? Before speaking about the floating structure, in 2013, we constructed a terrestrial pilot structure near the dam. So we are next to the lake, more or less on the same side, about 3 kilometers more to the north. On this structure here, we could test different modules, different technologies, monofacial and bifacial modules. The goal of these tests were to measure the impact on production, on the yield, the distribution of the production over the year, and especially the snow removal. We could here confirm the benefits of bifacial modules. We could determine an optimal angle, tilt angle between 30 or 35 degrees. The yield that was measured here is about 1,800 kilowatt hours per kilowatt peak. What is also interesting, since 2013, the Subsea, Gabi Friesen, proceeded to flash tests on these modules, and since 2013, there were no particular aging processes identified on this site. Based on these tests, we started simulation of the floating PV plant with the adaptation between the terrestrial pilot structure and the concept of the floating structure. We had to adapt a few parameters and could determine a yield for the floating structure of 1,400, more or less 70 kilowatt hours per kilowatt peak. The evolution from simulation to the effective production simplified like this. Our pilot structure with 1,800 kilowatt hours per kilowatt peak. Different parameters that were considered. We have near shading. The pilot structure, the row spacing was about 3 meters, and on the floating structure, we are only at 1.95 meters, losing therefore approximately 5%. The far shading, due to the near proximity of the mountains, where we lose about 7%. The albedo, on the terrestrial structure, we are on ground during the whole year. On the floating structure, we have 6 months a year where we're on water, so we lose the albedo effect during this time, losing again 4%. Tilt angle that is not always optimal, and string connection on the floating structure, whereas the terrestrial pilot structure was with micro optimizer. Therefore, we simulated yield for the floating structure of 1,470 kilowatt hours per kilowatt peak. Once the plant was commissioned, we have now identified one more parameter where we lose some production due to snow coverage. I will come to this on the next slide. These 3.5% bring the real yield of the installation to 1,418 kilowatt hours per kilowatt peak. This represents the benefits of more or less 30% compared to other plants in the plains. Those two parameters, snow coverage and the near shading, those are two parameters we can influence with during the conception phase for next projects. And we believe that on Lake Tool we could attain around 1,500 kilowatt hours per kilowatt peak. The snow losses, on one side we have snowfall. So even when the irradiation is low during during winter, the snow removal is working properly as forecast. As we can see here on this first picture, is 9 o'clock in the morning. All the panels are completely covered. 1 hour later, due to the irradiation of the back face, we have only 80% or 70% of the surface covered. And even 1 hour later, we are almost clear, like 10 or 20% covered. This is working quite properly, except during when we're at midwinter, around Christmas, New Year, around winter solstice. When we have when the irradiation is too low. We have we face another problem, which is snow drift. So we have some specific areas which are subject to blown snow, which deposit on our modules. And the problem is that this snow cannot be removed because the whole volume beneath the modules is already filled up with compacted snow. So we have some pictures of these situations. Even when the sun is shining, there is some snow remaining because the volume is filled up. This impacts naturally the production, the complete string where the panel is covered. Another effect of that is that with this additional mass on the module, we have some modules that tilt due to overload. Finally, what's the outlook for future projects? With this first floating PV installed on Lake Thule, we confirmed the technical feasibility, and we are currently working on an extension project on the same lake and on another lake as well. For Lake Thule, we plan an installation of 30.5 megawatt peak. The size is around 20 hectares. We completely designed or redesigned the floating structure, thinking about PV installation with double portrait. And we are also developing a horizontal axis tracking system, not only to track the sun and optimize PV production, but especially for wind safety, meaning that when we have wind gusts over 20 meters per second, our PV panels can lie down horizontally. We conducted as well a potential study for FPV and hydropower lakes in Switzerland. We selected 25 lakes, from which 11 were considered as favorable. On these 11 lakes, we could install or produce around 550 gigawatt hours per year, from which more than 200 could be produced during winter semester. Now we face a technical and legal framework that is missing. For the moment, our authorities cannot approve these new projects because of this missing legal framework. So we need development of the framework. There's an international development that is required to be able to give proof of structural safety for the retaining structures. This was it from my side. I hope that I could answer some of your questions. I'm at your disposal for any questions.
Yes, thank you for this very interesting insight with the experience of a floating alpine PV system. We have time for some questions here from the floor.
Hello, Andy. Thanks for the presentation. Leonardo Micheli from Sapienza. I have a question. How is a comment, really, I would like from you about the scalability. So now that you have this first plant, how is going to be easy to replicate to the 11 lakes you have identified? And which are the conditions you're more afraid of, like different snow loads, different depth of the water? Yeah.
The conditions I'm afraid of in special is snow load is not specific or is not that difficult to manage. The most difficult is water level variation, the anchorage system that needs to be adapted on one side, and on the other side is when the lake is dried, flushed, the interaction between the floating structure and the ground. The ground, we do not need a golf green, but we need a more or less flat ground that remains flat throughout the years of this plant. These are the most difficult points to address.
Is here another question? If not, we have one from online, from Kuma Bimavarapu. Other than the loss of production, were there any equipment damages due to snowfall?
Well, snowfall, yeah. We had some panels that were damaged either broken, either completely tilted because of snow overload. It's not the snow by himself that's damaged the panels, it's the snow accumulation, the snow drifts that broke some of our panels. But except from that, no, there was no other damage.
Okay, thanks a lot again. And I think we can so close the presentation part, and we pass to the panel discussion, which is coordinated by Leonardo Micheli from Sapienza Rome University. And we have 3 panelists, which is Gernot Orewski, speaker from before, Julien Chapon from Total Energies, and Silvana White from NREL.
Okay, so thank you, Gabi. Gernot, I want to talk you a bit again, about climatic condition, stressors. And I want to go back, to designing modules that are able to withstand, let's say, the most different conditions. Which do you think are the main challenges? So if we cannot do module-specific design, what shall we go after to make sure that, the modules can withstand, the variety of conditions we have seen today?
I would say the biggest challenge is cost. Because as I pointed out, we know how to make good modules. With a bit of luck, they withstand 40 years of operation. So we know what we can do. The panel is moving. But the thing is, and I think that's also related to what Bert showed yesterday in the meeting, that modules are a commodity and are not treated as an integral part of the energy system. So nobody's willing to pay more for a good module, and that's the biggest challenge. We need, to repeat that message, and hopefully sooner or later somebody will acknowledge it and be willing to do more. And on small level, it's happening. Like, in Austria, we have a module manufacturer that is providing PV modules that are fit for alpine climates, like thicker glasses and so on. Just, to have a product specifically for one region. But I would say this is just, at the beginning.
Okay, thank you. I think, it will be interesting if you, Julian, then, get in and, if you can guide us through, the process of selecting modules and components, designing systems from an industry perspective, right? So which are the priorities you identify when you design a new system, given the climatic conditions and so on?
Yes, so it's true from the industry perspective, this climate-specific optimization topic is moving slower than for R&D, and it's also non-uniform. Not every developer can spend time and resources in educating their developers, adjust their tools to address that topic. And it's also non-uniform in the development cycle of a PV project. Of course, we do it for resources estimation. We have to consider climate. We do it for design and layout, but mostly big considerations, I would say, like a high wind load, for example, or excessive soiling. But I wish we had a portfolio of modules tuned for specific climate, like you were saying. For yield estimation, yield assessment, this is the most important step, because this is the step where you calculate how much money you will make for 30 years. I guess this is where we need to make more efforts, because today we use a lot standard degradation rates, standard PLR, and we know that they are representative of moderate climates. So they are not always accurate for the projects we develop around the world. And for this year, there is a lot of improvement to make. And for O&M, I think here it's it's done also most of the time. It's quite easy to do, and yeah, it makes sense. For example, if for soiling, makes sense to consider this in your cleaning strategy, or even for performance analysis. Obviously, you try to do data analysis of assets from the same climate, same geography. Yeah. And for the cost, yeah, like you were mentioning, it's always for us, it's maximizing the energy yield, considering the land surface or the maximum capacity we can inject into the grid, and also minimizing the capex and opex. And on top of that, you need to consider electricity price coming from a power purchase agreement or from the market. And you need to make this equation and solve it. And for us, we solve it with the ROACH, which is a return of the return on average capital employed that we need to target. We have an internal target for that. Yeah.
Okay. Yeah, questions.
I'm interested in your calculation. What kind of degradation rates are you considering for the yield, and also like, okay, replacement of other damages, like when there is a hail or a weather event, or just, I don't know, car crashing into some modules, whatever. But, you know, this would increase your capex, but with more robust modules or better modules, you could have lower degradation rates. So do you consider that, or just say, okay, this is my yield for 30 years, and we say 0.5% a year?
So unfortunately, yeah, we need to consider standard rates most of the time coming from the datasheet. And we know it's not really accurate, but we need to do this because there is a performance warranty that is tied to this rate given in the datasheet. And, you know, the thing is, if you have a cold climate, for example, where you know that you will have a lower degradation rates than from a moderate. If you put this in your project and then you go to see a bank or investors, they might actually consider you are too optimistic and say that it's unrealistic. Sorry, so maybe they won't back you up. And on the other hand, if you also do a project in a very harsh environment, tropical, you put a more realistic degradation rate, so a hard on one, then you might lose a bid because the competitor will put the one from the moderate climate and obviously will have better figures. So it's complicated, I would say. Yeah.
So sorry, just building up. Would you trust your own data, or would you trust what is available in the literature? Where would you source?
So no, it's important to have literature very accessible for everyone. And on top of this, we do a lot of data analysis on our own fleet and try to balance a little bit to what is available on I would say on the market, but on the literature field, thanks to you guys, and also on what we can calculate on our own.
Thank you so much, Silvana. I wanted to ask you about one of the main shifts we are seeing at system level is probably the adoption of bifacial modules, tracking systems. So my question for you is, which are the factors we have to take into account? Again, depending on the location where we are when we want to design such systems.
Right. And yes, you're right. It is definitely very adopted now. And I want to start by giving a shout out to the latest IEA PVPS Task Group 13, which you're looking at the seminar report led by Joshua Stein on bifacial and trackers. So there's definitely a lot of that information there, but starting with the standard go-tos for optimizing a site, regardless if bifacial or not, but particularly bifacial, the ground coverage ratio and the clearance height and the albedo are very important on tracker systems. And so utility size scale on trackers, the GCR was around 0.3 for bifacials. It's perhaps lowering a little bit. So 0.25, we've seen that because the more space that you give it, you have more use of that diffuse light, right? In terms of clearance height, it has various benefits, and it's very important for bifacial. That's why we don't see it on rooftops. And it also helps with more temperature flow underneath the panels, and perhaps if you have dual use applications. So clearance height and albedo, right? So there's a lot of interest in locations starting to tailor their albedo and optimize it. Also in terms of tracking angles and the GCR, right? So if you go up on higher latitudes, you probably are increasing your GCR to do a little bit less backtracking at those angles. So all of these parameters are typically to do an optimization with the before you set up your site. Now, in terms of other factors, so algorithms for tracker companies, so there are some tracker companies, as you will see on the report, that are doing some more like diffuse content or bifacial algorithms. It's a little bit black box and really what they're doing. From our modeling, we can, for example, do a diffuse tracking algorithm where you set up, just like in monofacial systems, you set up your panel facing up and you get 1% in monofacial systems, extra radiance from doing that on a cloudy site, annual energy gain. And for bifacials, that goes a little bit up. So for example, modeling Seattle, it can be up to 1.4% if you have a high albedo. Albuquerque, the benefit is lower in the range of 0.4 to 1. So that's definitely a very common tactic to just phase them upwards. Now, a little bit more specialized on other points for specific climates, as we're talking about adapting PV and adapting trackers, right? So things that we've seen is on cold climates, don't use trackers that have hydraulic components, which there are a couple companies that do that, but the cold definitely doesn't play nice with that. We also seen frost heave, so that's when the racking, when the soil like heats up and cools down and hits and like thaws, right? And so that has made some of the racking just pop up if they're not that deep enough or well placed enough. So that's some experience that the racking companies go through too. In terms of the tracking, there's also snow algorithms that shed that light, that snow. So higher tilts will obviously make the snow slide off, right? As well as if you're doing frameless, that also helps. Bifacial also helps because then the back starts producing a little bit of energy and heating it up. But also the row spacing and clearance in snow regions matter too. If you have a lot of snow, it will start to slide down, but if the snow is already at that level, it will not really fall off the module. So you have to do some O&M and clean underneath so it continues to slide down, or to have a higher clearance. For desert, I don't have a lot of points, but UV is pretty strong. So cable management is important, and it's really a dumb situation to talk about zip ties on PV, but if they break and then you start getting tension into the MC4 connectors and then you start getting fires or issues on that, right? So cable management, and also we've seen desert locations have more of dry cleaning robots now. So having the rackings are designed to perhaps allow them to go between sections of the same row. So that connection systems, having that. We'll say final last thing, like windy sites and hail-prone sites. Obviously, we've been talking a lot about module quality, module thickness, having good algorithms to detect the wind and or hail, and go to stowing positions. So those are a lot of things, sorry. Thank you.
No, thank you so much. So the floor is also open to questions. So I wanted to check out if there are questions from the floor to the, yes, Gabi.
This is Josh from Sandia. Julian, I wanted to ask about the ability when you're building a large power plant to actually specify some of the module characteristics that you want. I mean, if you're buying a gigawatt of modules, can you go in and kind of customize them? Is that something that you do at Total?
It's not something we can't really do, to be honest. Even though we might appear as a big developer because we have, so for example, our target is to deploy 100 gigawatts of renewables by 2030. We are still a small player, and we need to secure capacity with the manufacturers. And we are buying now modules to be used in years from now, but we still don't know exactly what will be the modules. It will depend on the roadmap of those guys. So we try to adjust because we have access to a portfolio of modules from manufacturers we work with. But right now, as you could see, they are more declined by cell technology rather than really characteristics, especially for climate. So we try to adjust, but it's quite limited. But it's true that we are not in a position, we might think that really developers are in a position to force position compared to manufacturers, but I think it's the other way around. We need today to let them know that we will buy whatever they produce years from now. We need to make sure we have modules to be able to deploy all our projects.
I wonder if there's an opportunity to sort of build alliances because it's part of the problem is that you're small, you're a small customer to a large producer. But if you could somehow build alliances in maybe different regions with developers to really try to put pressure that there is interest in, making some modifications that are climate specific that would play a little bit more role.
Totally, that would make sense. Yeah, maybe pressure coming from R&D institutions also onto those manufacturers.
Yeah, let me see if I can get this right because there's a lot of parts to my premise here. So if you're a customer who's actually responsible for delivering electricity, you have the option to bypass the issue of changing module builds by simply buying a certain module, BOM and construction, placing it in a place with a high stress environment. Saudi Arabia comes to mind because it's both at times hot and at sometimes humid, and because it's hot and because it's humid, you'll see significant acceleration of any issues. PV modules are not expensive these days. I've talked to Trina Solar. You can buy. They say, well, if you like this encapsulant, sure, we'll sell it to you. If you like that encapsulant, sure, we'll sell it to you. No problem. Have it your way. So I guess I really don't see let me put this in the positive. How about that model? How about actually putting the module you like in a harsh climate, see if it works for you, and then buy more of it.
I don't know if someone wants to comment.
Yeah, maybe 2 years ago, we were visiting a Kalyon PV in Turkey. I don't know who knows Kalyon PV. And one day of the trip, we went to the Karapinar system that is 1.2 gigawatts. So that's the biggest system in Europe around. Okay, even it's in central Anatolia, but nevertheless, it was quite impressive, 25 square kilometers of PV modules. And the whole Kalyon PV company was founded. And for the first 4 years, they just produced to install this big system. Because the Turkish government wanted to have a part of the supply chain in Turkey. And so that's one of the few companies that are doing ingots, cells, and modules at the same time. And it was quite impressive to see this outside of Ankara, this factory, And I'm wondering why not more are doing this. And they try to do this for their location, find the perfect module. So examples are out there, but
yeah. I would like to add, because it seems that what you're proposing is to test the module before buying it, and
automotive does.
Yeah, but I guess we're switching so fast in our bill of materials and then new technologies that maybe perhaps by the time that you say, okay, yes, this is the one that we want, they will already be, I mean, also the supply chain will have changes and they do little changes to cut costs, and you really never know what you're going to be getting. So it's challenging, but it will be ideal, right? To be able to test it. That's why we do that accelerated testing. That's why we have the standards to have them pass and be in. Luckily, or that we are on a very big deployment PV. So sometimes we also don't get a lot of choices on what we get to deploy. Is just what's available, at least here in the US. So it's like, this is what we have. Okay, sure, I'll take it. We want to deploy it. So that reduces our negotiation power a little bit.
Okay. Kind of along those lines, because there's always this, of course, question of, yes, we can make a robust module, but we don't, because we're always trying to make things cheaper and we're deploying, trying to deploy at higher rates, et cetera. But I also wonder, and I'm not an expert in at all about how all the contracting, et cetera, works in terms of, when you're negotiating a PV utility plant, et cetera. But I would think that insurance companies could very much be driving this too, because if in the end insurance company says, I'm sorry, I'm not going to install or insure a PV plant that is in the hail belt in the US or Switzerland, et cetera, then it seems like manufacturers would kind of have to be forced to adjust. I mean, in the same way that fire risk has made certain homes around the world insurable, which is a problem. So could that potentially be something that drives towards more tailored bombs, whether it's glass, encapsulant, et cetera, to different areas?
I don't know, Julian, if you have any comments on
Well,
that.
I can only agree with what you say, that insurance companies today, they make developers pay more for if they install a system in complicated areas, and we have to bear the cost. I wish it would be the panels manufacturers, the module manufacturers, to actually create modules that are better suited for such environments. Yeah.
I think the problem is a little bit how the insurers know which modules are good and which are not. You can make a factory audit, you get to see shiny production lines where everything is polished to the end, but it doesn't give you any information about the longevity of the module. So I guess that's the biggest issue. You could do some IC testing, but we all know IC testing is not reliability testing. We could send Peter a sample, and that takes how many months to do all the circles? Few months, and that is already too much time. So I think that's the biggest issue here.
It's not too complicated to have a tool, for example, that says this, module has 3 millimeter versus 2 millimeter glass. And then could the insurance companies, anyway, this goes back to, I don't know how it's all related. As you said, the burden is put on the person that's building the PV plant to pay more for the insurance rather than it getting back to the manufacturer. But there are ways to at least measure or know some of these things.
Yeah, but that's the issue I think I brought up. It's transparency. We don't know nothing. And if there would be transparency and some sort of interchangeability between also multiple manufacturers or of components of materials, that you can say, okay, we use 3 different providers so that we don't have supply chain issues with a single provider. But then the product should be interchangeable. And automotive is doing that. We are not. And yeah.
And adding to that, I guess we've had really good success on our PV reliability workshop and Duramat activities of having insurer companies joining us because they're interested in learning our results. So that places a lot of the responsibility on us as scientists, not only to research the right things, but to be able to communicate them in a very concise way, right? But that also takes time. So we are trying, I think, all of us the best to find that.
Yeah, I was wondering also about your comment about insurance, is because it's not just the project developers that need insurance, it's also the manufacturers for the warranties. But I think one of the problems is the warranties are not really that valuable, right? Because it costs so much money to actually, I mean, the module's $60 and, it costs many more times that to actually replace it. So the value of the warranty is pretty useless. The other problem I think is at least in the United States, is the tax credits. The investment tax credit doesn't really value the reliability. It's just you build the plant, you get it commissioned, then you get your tax credit and you move on. So that's another problem I think that we could probably policy-wise try to shift.
Before Anna's the question, no, there are a couple of comments very interesting in the chat from 2 persons that are working in the insurance sector. So Mariam is saying that at FM they are actively testing the panels, And actually they're available, she left her email in case anyone wants to get in contact with them. And while Michael Perron says he's working in an insurance company, and there will be a push toward more resilient panels, chemically treated in certain zones, and more realistic tracking strategies for stow. Also, he highlighted that warranties can exclude, or force the exclusion of major events like hail and hailstorms. Unfortunately, due to time, we have to go to our closure. I want to give, the panelists the opportunity for some closing remark. We heard a lot. We had a very nice discussion, both in the room and in the chat. So which are the next steps in your opinion? Which have been the recent advancement, or are there any emerging technologies that you think can, improve adaptability and the reliability of photovoltaics in different conditions?
Okay, I'm just a small researcher in this world out, so I don't have any clue about how economy and the industry side works. But my wish for the future would be that we go away from just capex thinking and go more to, we have 25 or whatever lifetime, and think this whole cost over the lifetime, and that maybe a lower degradation rate over lifetime actually gives you more profit than lower capex at the installation of the system. So that's my hope for the future. Maybe I see it in 20 years until I go to rent, but yeah, we will see.
Yeah, I kind of agree on a personal point of view. Yes, for me, I think I want to say that developers they have this pressure from society, from governments to deploy as fast as possible, as much as possible, and we are just installing whatever is on the market. So, in my opinion, I think one big step would be if we can at least get several performance loss rates on a data sheet for one module. That would be great. So we can make projects that would be more realistic, and eventually have different modules for specific climates, one for tropical, one for desert, etc. Just like we start to see for different applications like floating PV, BIPV, agri-PV, etc.
Yeah, I don't know that I'm adding anything new to what's been said, because I super agree with both of this. But yeah, I think continuing, definitely, at least on the US, CEDOS has been pushing a lot for durability studies. That's like a big part of what we're doing, especially as we grow and install more, right? So continuing to not take out the finger from this line of high quality modules, not letting bad quality go out, perhaps increasing our communication and power to say, no, this is not working. And some of that will take experience and a lot of research, right? But there's some things that I think we already know in this room, and that we're still like, why are they still doing this, right? For example, the big modules trends or some other ones. So I don't know. I think in general, we are going on a good path with our reliability studies and learnings, but just need to continue that communication and research.
Thank you. Thank you. Please join me in thanking our speakers, our panelists. This closes our workshop today. Thanks everyone for attending. Thanks NREL. Thanks Silvana for hosting us. And I think the recording will be available soon. And you can find all the information on the Task 13 website, and hopefully soon our report. Thank you very much.